Okay, so now we've mentioned a few theorems. And just to summarize in slightly more sophisticated language, we take our curve x, we take the first Étale cohomology with coefficients in L, which we can also think about as the dual of the Tate module of the Jacobian. And then we'd like to ask, if we write down the corresponding L function, does this have analytic properties? So in this context, if I call this V, the L function of V is its usual definition of the product of all primes. The determinant, well, I have this representation. I can take identity minus the factor of p to the minus s, and then take the element of the Galois group that's Frobenius acting on V, then take this determinant and take its inverse. Maybe you want to do some corrections at bad primes, but this is more or less the right answer. So how do you kind of start to say something about this? Well, there's really only one way. Namely, you'd like to prove that this L function is equal to a different flavor of L function, where now this is coming from a different world, and now maybe on this side, you know how to prove the the analytic properties. And this was maybe one of the key insights of Langland's, was that this was really the way to proceed, where this pi was an automorphic representation, the sum group. But if we just, for example, start off with talking about elliptic curves, the corresponding automorphic representations we get are actually much more familiar, namely they correspond to modular forms. So let me just remind you of a few examples of modular forms. So everyone's favorite example is the Ramanujan delta function. So usually one notates q by e to the 2 pi I tau. And then this function has a beautiful product. Q, n is 1 to infinity, 1 minus q to the n to the 24, which I can just expand out. You can think about this as a Fourier series, q to the n times tau n, for n is 1 to infinity. You can start to compute it. Q minus 24q squared plus 252q cubed. If I was Don Zagier, I'd write out some more terms, but that's all I know. So this has the following property. Like all modular forms, it transforms in a certain way under this following Möbius transformation, where A, B, C, D is an element of gamma n, which is the set of matrices in SL2Z that are congruent to 1, 0, 0, 1 mod n. So in fact, for this group here, so let me write out the formula. C tau plus D to the power of 12 times delta tau. For all matrices, in this case, the level is 1. So in fact, for any element of SL2Z, it satisfies this transformation property. I want to write down one more modular form, which is f of tau. And it's going to be constructed just in some very simple way from delta. I take delta, then I take delta of 23 tau, and now the power of q up the front has become 24, so everything is a 24th power. So I take its 24th root, and I get the following expression. Now it's just 1 minus q to the n, 1 minus q to the 23n. And this I actually know a few more coefficients of. Q minus q squared minus q cubed plus q to the 6 plus dot, dot, dot. Okay. So of course, the first remarkable thing about these functions is that they exist at all. But Ramanujan, in fact, noticed a very beautiful property of these coefficients, probably just by looking at them. Namely, that he noted that tau of nm, of the product of two integers, was the product of the taus for all n and m that were coprime. And then, later on, Mordell proved that this was true. So how did Mordell prove it? So for these spaces of modular forms, once I choose a weight, which is what 12 is, and I choose a level, which is what n is, and maybe I impose some extra condition to do with the behavior at the cusps, or as tau gets big, I get spaces which are finite dimensional. And in fact, in this case of weight 12, level 1, and cusp forms, you have a one-dimensional space. And then Mordell observed there were some Hecker operators, he didn't call them Hecker operators, which preserved this space, and because it was one-dimensional, this was an eigenform, and because it was an eigenform, then the eigenvalue was equal to Tn, and because the product of these two operators for coprime things was the product of was T of their product, you immediately got this relation here. But then Hecker observed later, and perhaps more fundamentally, was that even when your spaces were finite dimensional, you could still simultaneously diagonalize all these Hecker operators, and whenever you have spaces of modular forms, you could always write them more or less as a sum of Hecker eigenforms which had this special property. So for example, this form here also satisfies the same property, and now because I wrote enough coefficients, you can see that A2 times A3 is A6. Now, if you look at this, you see that you have a transformation between tau and -1 on tau. And that's not quite true for all gamma 0 n, but nonetheless, just by using the functional properties of this, if I write down the sum tau n on n to the s, in fact, this has an analytical continuation and satisfies the functional equation. Similarly, same with here. So that's coming from the modularity property. On the other hand, because of this factorization property, it has more than just a functional equation. It also can be factored, just like Euler factored the Riemann-Zeta function into an Euler product. And in fact, this can be written as the product of 1 minus tau p times p to the minus s plus p to the 11 times p to the minus 2s to the power of -1. Similarly, I can write down the corresponding thing here. Let me just call the coefficients an. I have something very similar, 1 minus ap, p to the minus s, plus, well, this 11 here was coming from 12 minus 1. This form here is actually of weight 1, and so I should get 1 minus 1, which is 0, but still a quadratic residue symbol comes up. This is the same quadratic residue symbol as in the last talk, s to the power of -1. And in fact, for all modular forms, rather all, at least once you make them eigenforms of these Hecker operators, have these Euler products of this shape here. So there's another thing that has an Euler product of this shape. If I take a two-dimensional Galois representation, and I take the trace of a 2x2 matrix corresponding to Frobenius, I also have an Euler product that looks remarkably like this. And so that suggests that associated to modular forms, there might exist Galois representations. Namely, exist exactly the objects here, the linear algebra objects, vector spaces of a QL, with some action of the Galois group that we got from geometry. And so now things are getting interesting because we have two sources of Galois representations, one coming from geometry and one coming from something completely different, namely modular forms. So a theorem basically proved by Shimura for k is equal to 2, but in fact his argument can really be made for k big or equal to 2. Then Deligne for k big or equal to 2, but he proved much more about it. And then Deligne and Serre for k is equal to 1 is associated to a modular form that there exists a Galois representation. Well, maybe now f is not necessarily that f, but it's a modular form. And I choose a prime L. And this is mapping from the Galois group of Q to GL2. Well, it's not quite QL, because when you diagonalize these Hecker operators, sometimes you have to go beyond Z and take the integers of a number field. So you're in good shape if you take the algebraic closure here. Okay, well, I should finish this statement because this Galois representation should have something to do with the actual modular form. And namely, if I take exactly the corresponding expression, determinant of the identity minus p to the minus s for abelian at p on this representation, I get 1 minus ap p to the s minus s plus p to the weight minus 1 times some Dirichlet character times p to the minus 2s. Okay. Okay, so exactly what it says is that this Euler product, which is coming from this remark of Ramanujan from an automorphic object, is also coming simultaneously from this two-dimensional Galois representation. And if you remember where we are, in the case where at least for genus 1 curves, where the H1 is two-dimensional, we'd like to say that our L function has some nice properties. And here we have a whole source of Galois representations with nice properties, which in particular have L functions with analytic continuation. And so very naturally, you might ask, say, let V come from geometry. So what do I mean come from geometry? I mean I take some proper smooth algebraic variety. I take, it's a tiled cohomology. I get some Galois representation, and I take some two-dimensional chunk from that. And then, okay, so associated to this, I have a Galois representation. So you can ask, does there exist a modular form F such that this Galois representation associated to L, so this should be a vector space 2 dimensions over QL, such that the Galois representation for some modular form is the Galois representation associated to V. In other words, if we could take just our two-dimensional Galois representation from geometry and show it came from a modular form, we'd be in great shape because the L function of a modular form is something that we can tell has an analytic continuation. So it turns out there's one obstruction, namely, if I take this Galois representation, well, there's only one element of the Galois group we understand. That's complex conjugation. Well, maybe there's the identity as well. So this has order 2. So its determinant is always plus or minus 1. It turns out for a modular form, the determinant is always equal to minus 1. And so the minimalist conjecture is that if this determinant is minus 1, then there exists an F. And this is really what Wiles proved in the case where V specifically came from elliptic curve over Q. But I think, at least in this incarnation where I'm really now taking V to be motivic, is that this is now a theorem. So of course, it follows the methods of Wiles, but I think the final resolution was due to Kissen and also to Carré combination at Vantin-Berger. Serre's conjecture. Okay, so that's great news. And so now the question is, well, let's do this with a 4-dimensional representation coming from, say, a curve of genus 2, or why not do it with anything at all? Well, before doing that, I want to just delve a little bit into the details, or if not the details, maybe the phenomenology of Wiles's argument. Because understanding not only how that works, but how it fails to work is in fact crucial for understanding what to do in a general case. Okay. So let's talk about Wiles. You have a 2-dimensional representation valued inside this group here. This is a profinite group, so for compactness reasons, you can actually always make it land inside, let me now call this GQ, it's just the same thing, always land inside GL2 up to conjugation of the integers in the algebraic closure. And then once you have this, I can take its reduction, and they're going to map to now a finite field, and I get the so-called mod L representation. Okay. So what's true is that if you have a modular form, so let's suppose we have a modular form, this Galois representation, again, if you believe the Tate conjecture, this Galois representation should really be telling you a lot about the underlying situation. This Galois representation should know a lot about F. So if, for example, one thing that's true is this is unramified outside some finite set of primes to do with the level and the prime L that we're choosing. So that's a kind of easy condition. But a much more subtle condition is when we restrict this representation to the local Galois group at the prime of the residue characteristic we're interested in. This knows about the weight. In fact, well, maybe I should say the weight and the level at P. So usually when you think about Galois groups and you think about decomposition groups, they're kind of simple and not very complicated. But for these p-adic representations or L-adic representations, there's actually a huge amount of information that goes into understanding these things. And in the last talk, I talked about Hodge theory. Something what's going on here with the Tal cohomology is a p-adic version of this, or maybe here I should call it understanding these representations goes under the banner of L-adic Hodge theory. The question is, how can you tell from this representation whether it came from something whose level was prime to P or not? And it's a somewhat intricate business. Okay. But back to Wiles. Okay, so what Wiles wants to do is he wants to fix this row bar and then look at all lifts. So what does a lift mean? A lift is just exactly like this, a map to characteristic 0, which reduces mod L to our original thing. Look at lifts. I'm going to use the word look twice. That look, maybe I should have said appear, modular of level. Well, I maybe have fixed a level n and fixed a weight k. So a really reductionist way of explaining what Wiles did is you had Galois representations, you had modular forms, you counted both sides, and you got the same number. Now, there are infinitely many of both, so you have to kind of restrict to some finite space of modular forms. And then you want to show that all these lifts, as long as you impose some local property that makes them plausible, again, here we have a minimalist conjecture, that was due to Fontaine and Mesa, as long as you impose properties that are necessary for modular forms, maybe you hope you always get modular forms. Okay. So there are two very strange things about this story. If you're used to the story about Serre's conjecture, the thing you would worry about is, well, how can I show there's only finitely many lifts? But there's also a very natural question, which is if I didn't start with something in characteristic 0, why should there be any lifts at all? So I wanted just to kind of say a few things about the phenomenology of why we expect maybe this set of lifts to be finite. So again, here's an argument that goes back to Fontaine and Mesa, and it's a kind of reality check on conjectures of this form. Okay. So in order to understand this, one thing we have to understand is we start with our row bar, and then we want to look at so-called deformations here to characteristic 0. Or either just deformations of this Galois representation, and here thinking about it as the Galois group of Q. So again, maybe I should have imposed here, I don't want to give myself ramification outside N. And essentially, I want to try to parameterize all Galois representations with a fixed row bar that lift to characteristic 0, or even just all deformations at all. And so why might you expect something to exist of this form? Well, of course, if you just take a finitely generated group, you can always write down a representation variety of that group just by you take the generators, map to various polynomials in matrices and polynomials, and you take the relations, and that gives you equations on the polynomials. You don't quite get that here because this is a topologically finitely generated group. So instead you have a more infinitesimal version, but you should really think about this as just being some nice space. And in fact, in the context of modular forms, you could even think about it as a nice space that has dimension equal to 3. If you even think about it as a 3-dimensional ball, you wouldn't be going astray. Okay. So what is it that we want? We want to impose the condition that the local representation has a very nice flavor. So what we should do is we should map to the local deformation space. So here, the deformation space of rho bar restricted now to this decomposition group at L. Okay. So this map, in fact, this is generally a finite map. So you wouldn't lose so much by even imagining you have an inclusion here. All right, so you have this space, and inside here, you want to capture what it means to come from a modular form of weight k and level gamma 0 n, but in particular, you're capturing your weight k, and maybe you're capturing the fact that the level is prime to p. And so in there, you have some nice locus. So here's the locus of nice representations. And what you're interested in doing is looking at the intersection of this with this nice locus. And first, well, of course, if that intersection is infinite, you're in bad shape of showing that there's finitely many points here. So one way to do that is just to do a kind of check on the dimensions of these spaces. So what are the dimensions of these spaces here? Well, I'm going to put in a framing and then somehow extract it here so I get the numbers correct. So the dimension of this space is 6. Oh, okay. I'm going to fix determinants here for those who know what I'm talking about. And here I get 2. I fixed that. So here I have 6. So what is this locus of nice things? Well, of course, what do we mean by nice? We have some weight k involved. And so here's what happens, is that if k is bigger or equal to 2, then the nice locus has dimension equal to 4. And so that's good. If you intersect a 2-dimensional space and a 4-dimensional space inside a 6-dimensional space, it might be reasonable to hope that the intersection is finite. But in fact, if k is equal to 1, then the nice locus actually has dimension equal to 3. Even better from one perspective, but maybe worse from another perspective. At least it's convincing to say that maybe the intersection is going to be finite, but it actually puts the kibosh on a whole kind of strategy of Wiles' method. So what Wiles certainly does is he tries to show that there are enough modular forms to account for all Galois representations. But what happens when k is equal to 1? Well, one way to think about this is that there are many fewer Galois representations that you expect. But it turns out there are far fewer modular forms of weight 1. And there's not really somehow, obviously, the weight 1 forms to account for all the Galois representations. And so at first blush, this is maybe a little bit surprising because from the analytic definition of modular forms, just in terms of sections with a functional equation, there's nothing really different between k is equal to 1 and k bigger than equal to 1, or bigger than equal to 2. So how does one account for the difference? So to do that, we have to think about modular forms more algebraically, just slightly more algebraically. All right, so a modular form, it's a function in the upper half plane, which, when you transform a point tau to a tau plus b on c tau plus d, it has some multiplier character. So if I take the quotient of the upper half plane by this group, and then maybe I compactify it to give me a nice space, I get a modular curve. And so I don't get a function on this modular curve. Rather, I get a section of a line bundle. And so modular forms correspond to sections of powers of some nice single line bundle omega that's exactly capturing this monodromy of picking up a c tau plus d when you kind of go around. So of course you get this power here. Even from this description here, there's not so obvious why this looks different when k is bigger or equal to 2 or when k is equal to 1. But in fact it is. And one reason, and let me just ignore the cusps, Oh, no, let me not. So is that the square of this sheaf is basically the canonical bundle. Rather, the canonical bundle, this is telling you about, in fact, cuspidal modular forms, and so I have to allow myself kind of log poles at the cusps, poles order 1. And so what that means is if I take the first cohomology of xn through k, this vanishes for k bigger or equal to 2. But in fact, if I take the first cohomology of omega to the 1, well, said duality is somehow relating cohomology of a line bundle to the cohomology of the canonical bundle divided by the line bundle. And if it's basically omega squared, this is relating H0 of 1. Well, this is related to H0 of xn. So if you ever have modular forms of weight 1, in fact, you always get classes in H1 as well. And so this manifests itself in many ways. One manifestation is if you have a modular form mod P, if you're in high weight, you can always lift it to characteristic 0. This is not true for weight 1 forms. If you have a modular form of weight bigger or equal to 2, or you're looking at the space, you can compute the dimension of the space using Riemann-Roch. You have some nice formula. When n grows, this grows. This, you can't compute the dimension. Well, rather, you can compute the dimension of this minus this, which is going to be not very interesting. It is some number related to the cusps, but you're just counting Eisenstein series. So there's no reason why you can expect this to grow at all. And if you know something about weight 1 modular forms, you can even show that you don't expect it to grow at all if you choose Pauli. Another way, again, just to emphasize this point, if cohomology is in 1 degree, you always expect when you have covers that cohomology goes up by a lot. Basically, you should just think of the Euler characteristic, should multiply by the degree, and so if all the cohomology is in 1 degree, it's all accounted for by the Euler characteristic. But if you have something in more than 1 degree, well, you get something like 0 times k is equal to 0, which is not very interesting. So the moral of the story is that in this situation here, so here the virtual dimension, which is just the kind of expected dimension, was 0, and here the virtual dimension was equal to -1. And so the moral of the story is that this -1 is exactly accounted for by having cohomology occurring in ranges 0 to 1. And that moreover, by a modification of the Taylor-Wiles method, which is due to David Garrity and myself, you can, at least if you give yourself enough optimistic conjectures and happy coincidences and things that you expect to be true, you can really prove that in order to get a modularity, what do you need? Well, on the one side, you have the Galois side. And here you have some virtual dimension, which it turns out, I'll write it as minus L0. This will always, in accordance with the Fontaine-Mazur conjecture, it's always less than or equal to 0, but it's often negative. And then on the automorphic side, well, maybe what is it that you want? Maybe in some sense you have to go beyond actual automorphic forms, and you have to look instead at the cohomology. And so rather you have to replace automorphic forms by some version of cohomology, and rather what you'd like to get is a complex. Find complexes which have the property that their amplitude is exactly of length L0, and such that the cohomology of this complex is now something for which you can associate Galois representations of the right shape. Okay. So the goal, in order to prove a modularity theorem, is that in your situation, well, somehow you have to come up with a source of Galois representations associated to a complex. So just to say, of course, in the case of forms of weight 1, it's basically given to you already. It's just the complex associated to omega, and when you take the cohomology, you get exactly this H0 and this H1, but you get more information because, in fact, when you think about this complex and you think about this modular curve, you can be careful and put some arithmetic structure on it, and you get back not just complex vector spaces in this cohomology, which only tells about automorphic forms, but you get torsion in the cohomology, and that torsion is carrying interesting information about Galois representations. Okay. So one question is what is L naught? So let me just put ourselves in a situation in which that question makes sense. So we have to give ourselves a residual representation. Okay, so let's suppose we have a residual representation of the Galois group of a number field and mapping to, let me just say, the dual group of G and FP bar. So I'm just imagining G as some nice split reductive group, and G dual is just the Langlands dual. If you want to, you could just imagine G as GLN, and G hat is also GLN, and that would still be a very interesting case. Okay, so associated to this, we have a few things. So what is it that we have to say? Well, we have to choose a weight. So in the case of a modular form, the weight was just an integer. But in general, so this will just be a weight. This will just be a usual weight. In other words, a character of the torus of G. So it's just a weight for G. Okay, so for example, for modular forms, you're talking about weights for SL2, and the representations of SL2 are just the kth symmetric powers. And then, of course, there's a horrible fact in automorphic forms that weight, there are three definitions of weight. A modular form of weight k, it can also have weight k minus 1 or weight k minus 2, depending on how you think about it. So there's a weight. Another piece of data that's important is what complex conjugation is. So I can think of complex conjugation, well, it's acting via the adjoint representation on the Lie algebra G hat. Okay, and these are basically the two pieces of data that we need. And then we can ask, well, with such a rho bar, of course this only makes sense here for V dividing infinity, where FV is isomorphic to R. Right? There's no complex conjugation at complex places. So even just from this information, I can write this L0. There are three terms associated to this L0. There's an L0, maybe I'll say associated to P, which is to do with this weight, plus an L0 at infinity, which has something to do with complex conjugation, plus an L0 to do with the group G. Okay. And so this L0P, this is always bigger or equal to 0 with equality if and only if this weight is sufficiently regular. So if and only if, for example, the invariants under the Wiles group are just trivial. So only if this is regular. So for the case of modular forms, that means k is bigger or equal to 2, because the highest weight of the trivial representation is, of course, fixed by the whole Wiles group. Now, of course, you can give some, if you look in the notes, you'll see some formula for it in terms of stabilizers and Wiles groups of levies, but it's not so important here. The equality is only when this. When I look at L of 0 infinity, this is always bigger or equal to 0. And equality when? Well, if you look at involutions of G hat, there turns out to be a unique minimal involution of most negative trace. So the most number of minus 1s on the adjoint. So only when rho C is as odd as possible. So it minimizes the trace of C acting on this adjoint. That turns out to give a unique conjugacy class. And then finally, there's the L0 to do with the group. And, well, rather, this is a sum for all v. So this is always bigger or equal to 0. And it's only equal to 0 if and only if what? Well, all the v have to be real. So f has to be totally real. Okay, there's one exception that you're going to see in a moment. But f, maybe I should say it this way. Well, okay, no. Yeah. Fv is isomorphic to R. And when I take the group and I take the real points, this has discrete series. So in order for L0 to be 0, I need three simultaneous things to happen. I need to be in regular weight. I need to have something as odd as possible. And I need to be in a group with discrete series. And these are, in fact, exactly the three conditions in which the Taylor-Wiles method, that's kind of done originally by Taylor-Wiles, but certainly extended by Clauzel, Harris, Taylor, exactly where they applies. So, of course, here I'm not worrying about various twisted groups, but this situation when they're all 0 is exactly what happens only when you're in the case of Shimura varieties, and only when you look at automorphic forms contributing to the Étale cohomology. So weight 1 forms, they contribute to the coherent cohomology of modular curves, but not to Étale cohomology. Okay. Okay. So now, what does my method with David Garrity kind of suggest? It suggests, I mean, you somehow, in any situation, just have to come up with a complex of the appropriate length. Maybe I should just actually compute this L0. Let me just do F is equal to Q, and rho bar to GL2 FP. So there's 4 cases. There's K bigger or equal to 2, K is 1, and there's complex conjugation odd and complex conjugation a scalar. So here is 0. Here we get a 1 factor coming from the fact that the weight's not regular. Here we get a factor coming from the complex conjugation, which is 2. And here we get a factor, which is 3. Okay. So there's actually another example I wanted to do, which is one-dimensional representations. So one-dimensional representations, well, there's only basically up to twist one-dimensional representation, which is the trivial one. And in this case, the invariant you can compute is R1 plus R2 minus 1. Okay. So again, if you want to try and prove modularity for one-dimensional representations, I have to somehow find a space where, associated to the cohomology, I can find a complex in which the cohomology, at least the ones I'm interested in, is just supported in these degrees. But in fact, there's a very natural complex, a very natural space associated to this, namely the Arakelov class group. Right? I mean, of course, if you just take the Adele class group, then, well, of course, I want to cut out something at finite level, and then I want to cut out maybe some compact subgroups at the complex places, which is just getting rid of these S1s. And what these spaces are, these are basically, well, there's always this contractible copy of R that I can ignore, is basically S1, well, a bunch of copies, but S1 to the R1 plus R2 minus 1. And so associated to, well, of course, the cohomology of this has an action by the Ray class group, and so it has Galois representations there. And so you can turn, I mean, it's certainly a little circular in the end, but you can give a proof of modularity lifting for GL1 in this optic. And that's something I did in detail of the notes, not because it really tells anything for GL1, but it helps to explain the mechanism of what is going on. Okay. So now, what we have to do to prove modularity of abelian surfaces. Well, what's the situation for abelian surfaces, or just Jacobians of genus 2 curves? Well, I have GSP4 as the group. So GSP4, it does have discrete series. Abelian varieties, the complex conjugation will always be right. But abelian varieties, this is going to contribute something, because the Hodge-Tate weights of an abelian variety, 0, 0, 1, 1, it's not the most regular weight. All right? So the stabilizer in the Weil group is non-trivial. And, well, if I take corresponding to abelian varieties of F, I certainly want this to be totally real. Then, in fact, L0 is equal to the degree. Okay. So I have to construct some complex. Well, of course, I'm at least, and this is very fortunate, in the situation in which there's a source where I can expect to find the corresponding things. Namely, if F was Q, there's the Siegel threefold, which is the moduli space essentially of abelian surfaces. And that object is a Shimura variety whose cohomology, just like weight 1 forms were associated to representations when k is equal to 1. Here, so if I just take, for example, the Siegel threefold, so there now turns out to be a coherent line bundle, let me just call it omega squared, such that Siegel modular forms of weight 2 contribute to the cohomology in exactly these 2 degrees. So here I'm doing F is equal to Q, so L0 is equal to 1. So it's just like modular forms of weight 1, right? Again, if I take omega cubed or higher, this vanishes, and I'm in a regular situation. But for omega squared, there is some H1. So there are a bunch of things you have to worry about. Well, if I knew that H2 vanished, I could just take the complex R gamma x omega squared, and this would basically be correct. I'd still have to prove some facts about Galois representations associated with torsion classes that are, in fact, non-trivial, but at least gives me the type of object that I'm going to look for. All right, but I still need to prove that H2 vanishes. So how do I do that for a modular curve? Well, for a modular curve, I'd like to say that H2 of a modular curve vanishes. So it turns out that for curves, it's not so hard to prove that the H2 vanishes, especially of line bundles. But for threefolds, it's a little bit harder. And in fact, I should say we don't prove that H2 vanishes. And in fact, it doesn't even vanish. Which is one obstruction to proving it vanishes. In fact, we only really need to prove it vanishes, since I'm now in the last few minutes, I can start being more technical. We only need to prove that this H2 vanishes after localization at a corresponding maximal ideal. So how do we deal with this situation? Well, I want to take you back to a simple situation for modular forms in which the same things happen. I kind of create this bit artificially, but it's still true. Namely, let's suppose I want to do a modularity result for weight 2 modular forms, but using coherent cohomology. And let's, instead of using omega squared, I literally used H0x. I used this thing here. Well, then H1 of the canonical sheaf really doesn't vanish. I mean, that's sort of non-zero. It's one-dimensional by stereoduality. Now, of course, when I localize at M, I certainly expect it to vanish. But it's maybe not even so hard to prove. But in this situation here, what happens is that there'll be some weird non-tempered automorphic forms contributing to H2. And so even in characteristic 0, it's a bit hard to show it's trivial after localization at M. Even worse, there could be some torsion that you have no control over. So is there a way that even just in this context, we can make our lives easier when studying this complex just associated to this? So in fact, for modularity of modular forms, there's a theme that has been around for a long time, which is to think about ordinary modular forms. So what is ordinary modular forms? Well, I take X, and instead I think about modular forms over the ordinary locus. So what is the ordinary locus? It's something affine inside there. Yeah, this is all modular forms. Yeah, I'm trying to prove that weight 2 modular forms are modular. No, Galois representations. So what's good about the ordinary locus? Well, if I look at the ordinary locus, because it's affine, I get a complex that's supported in weights 0, 0. So that's great. Right? I've killed off this horrible H1. Well, of course, but these are going to be quite different. I mean, I have something H0, something affine. This is huge and infinite dimensional, and this is not. But of course, we know when we take the ordinary locus and look at modular forms, we don't look at all modular forms. We take an ordinary projector, and amazingly, that gets us back down to a finite dimensional space. And so in fact, once we take ordinary parts on both sides, we in fact have an isomorphism between these two complexes. I mean, we're just recovering that the space of ordinary weight 2 modular forms are classical. It's a result of Hida. But the great news is by working with this open affine, we've killed off the higher cohomology. So that gives us the right amplitude. And then by thinking about ordinariness, we've now related to here, which gives us the finiteness. So of course, that can't work here for the Siegel threefold, because if we work on the ordinary locus, we kill off the H1. So we exploit some new constructions due to Vincent Piloni, who came up with a paper that really started this project. So again, I can think of X. Maybe now I'm thinking of the Siegel threefold. This is three-dimensional, but of course there's some analog of this in higher dimensions. And so maybe I want to look at the special fiber. So the ordinary locus would correspond to, say, looking inside here of this space. Well, I'm so used to it like this. It's the ordinary locus. It's the part where these abelian varieties have p rank 2. Okay. And so it's just 1 for special fiber, mod p. Yeah. So of course this is affine, and the complement is, I'll call it, say, x less than or equal to 1. This complement is just the 0 locus of the Hasse invariant. But now I can go deeper into the stratum. I can take a secondary Hasse invariant, and then what will the zeros of the secondary Hasse invariant be? They'll be the supersingular points. And so instead of removing all the p-rank locus, instead I could take the part where I've just removed the supersingular locus. So this is a little bit misleading, but somehow I've kind of removed something of codimension 2. So this is no longer affine. But in fact, it's covered by 2 affines. And it's literally true that, I mean, we have to work with the toroidal compactification, but of course, in the minimal compactification, it's covered by 2 affines, and that's good enough for our purposes. And of course, we want to work maybe in characteristic 0, but you can reduce things by Nakayama to the special fiber. And so then what you might hope is that now when you take this complex, you can compare it to the complex of this object here. And by taking some suitable ordinary projector, now you have to define ordinary in a slightly different way. Now if you could show that these complexes are the same, well now great, because this is covered by 2 affines. Its cohomology has amplitude 0, 1. But in general, it could be infinite dimensional. But if this ordinary projector now cuts it down to this, you're now in good shape, because now you've basically shown that the complex you have has the right property. So that is, in a nutshell, the strategy of the argument. Now, for technical reasons, of course, our proof is not the ideal proof. It involves lots of sort of tricks to avoid ourselves from these complications. And we don't actually prove this. We sort of prove enough replacements to get by. But morally, this is what's going on. And perhaps that's a good point to stop.
Are there any questions?
So the whole starting point is there has to be some cohomology somewhere that sees the things you're interested in. So with weight 1 forms, you can't use a tau cohomology, but it turns out you can use coherent cohomology. Here, it just turns out that you can see these single modular forms. If you go to something of genus 3, you end up with the automorphic forms, conjecturally, that look basically as bad as mass forms, and they're not associated to any cohomology. And so, of course, the method works as long as you have the complex, we just don't know where to find that complex. Yeah, no, yeah, so because of course you're intersecting things which the virtual dimension is minus L0, but that occasionally there exist things, and so it must be a derived intersection. And the derived intersections are exactly the cohomologies in all these degrees. I don't think I mean, that's the same thing. It's the same thing, but yes. I mean, of course, with these not directly. I mean, you could also do something which you could have used completed cohomology, and you'd also, again, you expect the same L0. And Thorne and Hansen has some reinterpretation of Akshay's thing in that optic, sort of, and so it's sort of persistent throughout the whole thing that you kind of see this L0. And does that play a role in the structure? No, I mean the structure of the proof. I mean, of course, all of this related, but perhaps not sort of directly. I mean, I would say that to some extent, Akshay's thing was perhaps after what David and I did, and sort of reinterpreting that in a kind of derived and sort of new and very interesting way. So. Oh, so that was after. Well, so at least the basic idea was for David and I was from 2011. So we had to wait for sort of, at least in the case I did mention, for sort of Peter Scholzer and Anna Karyani to prove some results to actually get some facts, but yeah.